In this video, we're going to be talking about centroids. So the context is that we have a thin metal plate of constant density and constant thickness. So something like the metal plate that we've got in this picture here. And what we're trying to find is the center of mass, otherwise known as the centroid. And in symbols, we're going to write that X bar, Y bar. So a more typical example would be if we had, say, a thin metal plate shaped like this, and we'd be asking, what are the coordinates of the centroid? So let's take a look at how the formulas work. So to get X bar, the X coordinate of our centroid, we're going to go 1 over the area of the metal plate times the integral. We're integrating over the entire area. What we're integrating, XE times dA. So we'll talk a bit more about this XE in a minute. Similar formula for Y bar. Y bar is going to be 1 over the area times the integral over A of YE times dA. So in order to make sense of these formulas, we have to understand what these X sub E and Y sub E represent. So they represent the centroid of a slice. And the idea is that depending on the problem, we may choose to use vertical slices or we may choose to use horizontal slices. So let's break this down into 2 cases and we'll just figure out what XE and YE look like in each case. Let's talk vertical slices first, since that's usually our go-to. So imagine that our area or our metal plate looks something like this, and we decide to figure out that area using vertical slices. So X sub E then, the average X value along that slice is just going to be X, because when you're taking a vertical slice, X is constant. The X values are the same all along that slice. But the Y values would be varying. So to get Y sub E, which is the average Y value along your slice, you just go Y bottom plus Y top over 2. So you're just averaging your top and bottom Y values to get Y sub E. Okay, then let's run through the same kind of reasoning for horizontal slices. So maybe we'll have a region that looks something like that, and we'll decide, oh, maybe horizontal slices would work well there. So we could think about the area using horizontal slices. So X sub E and Y sub E represent the centroid of just this red slice here. Let's talk about Y sub E first. So Y sub E is the average Y value along the horizontal slice. Well, since this is a horizontal line, the Y values are going to be constant all the way along that line. So we can just say Y sub E is Y. But for X sub E, we would need to think about averaging the endpoints of the slice. So we would need to say X left plus X right over 2 to get the average X value along the slice. So to summarize what we've said here, the 2 key formulas that we're going to use for finding the centroid of a thin metal plate are these 2 formulas that we've got up at the top. And then what we do is we usually figure out X sub E or Y sub E just specifically for the situation that we're looking at. So with that, let's jump into an example and we'll see how the whole process works. So we're looking at the region bounded by the parabola y equal x squared and the line y equal 9. Let's just make a quick sketch here. So if we sketch our parabola, by the time we get to x equal plus or minus 3, we're up here at y equal 9. So let's say our parabola passes through these points, and that way we can make a quick sketch there. Okay, so I'll just highlight the region that we're interested in, so this entire region here. So imagine that this red region represents a thin, flat metal plate, and we want to find the centroid of that metal plate. So first thing we should do in any problem is think about symmetry. See, right off the bat, we're going to be able to say that X bar equals 0. And because the left and the right side are mirror images, we know that the center of mass is going to lie along this center line, which is the line where X equals 0. So based on that, we can say X bar equals 0, and sometimes we'll say by symmetry. So that massively cuts down on the amount of work that we need to do. That means that the problem really comes down to finding Y bar. So the Y coordinate of the center of mass. So we're going to break this down into steps. First thing that we need to do is find the area. So we'll say area is going to be the integral of, well, let's think about whether we want to do vertical or horizontal slices. I would say vertical slices would work just fine here. So we're going to say area is the integral of y top minus y bottom times dx. So with that, we can put our detail onto our integral. So we're going to be integrating from -3 to 3. Y top is 9, subtracting off y bottom, which is x squared, and we're integrating with respect to x. So we're going to have 9x minus x cubed over 3, and we're going to evaluate that at 3 and then at -3. So subbing in 3, we're going to have 27 minus 9, and then we're subtracting off the value at -3, which is going to be -27 plus 9. So overall, what we're getting is 36 for the area. So that's what I would consider to be the first step. Now let's jump ahead a little bit and just think about what the formula for y bar looks like, and that will tell us what our next couple of steps should be. So based on our discussion from a minute ago when we wrote down the formula, we said y bar would be 1 over the area times the integral over a, so that just means integrate over your whole region. And what are we integrating? Y sub e times dA. So the next step that we need to do is we need to think about what is y sub e in this context. So that'll be step 2. So step 3 will be to figure out this integral, and then in step 4 we can divide that by the area to get y bar. So I might just outline those steps here. So step 2, we'll figure out ye. Step 3, we'll figure out the integral of y sub e dA, and we're integrating over the entire area. And then in step 4, we'll get our y bar and we'll have our answer. Okay, so that's the plan. So let's go back here to step 2 and figure out y sub e. So I'm just going to draw a quick picture on the side of what our region looked like this. And we decided in step 1 that when we were figuring out the area that we were going to use vertical slices. So let's say you zoom in on this slice here and you say, what's the y coordinate of its centroid? Well, it's just going to be y bottom plus y top over 2. So anytime you're using vertical slices for the problem, y sub e would be y bottom plus y top over 2. In this particular problem, we said y bottom was x squared. We said y top was 9. So we're just getting x squared plus 9 over 2. Now, we didn't need xe to solve this problem, but if you were in a situation where you needed xe and you were using vertical slices, you would say xe is just x, because for any vertical slice, the average x value along that slice is just going to be x. So not necessary, but I just mentioned that for the sake of a full discussion. So let's think about what we're doing here. We're supposed to take the integral of ye times dA. So ye is what we just figured out in the previous step. It's the y coordinate of the centroid of a slice. And then to get dA, just look back at what you did in step 1. So dA is whatever you integrated to get your area. So this stuff here, this was our dA. So that's actually why we do the area in step 1, so that in step 3, when we need to calculate this new integral of ye times dA, we already have dA figured out. So dA is just the thing that you integrate to get your area. So that is 9 minus x squared times dx is our dA. Okay, and then when we say integrate over A, that just means integrate over the entire region. And effectively what that means is just plug in the same x values that you used in step 1. In step 1, we integrated from -3 to 3, so that's still going to be the correct x values to have on here. So now that we've got everything plugged in here, we're just going to do a little bit of algebra to get this cleaned up. What I would do is bring this factor of half out in front. So we've got half times the integral -3 to 3, and then we'd be integrating x squared plus 9 times 9 minus x squared dx. And then what we could do is just expand out this integrand. So let's expand this part out. We'd have 9x squared minus x to the 4th plus 81 minus 9x squared. In other words, when we simplify that, that would just become minus x to the 4th plus 81. And that would be integrated with respect to x. So let's continue that integration on a new page. All right, so I've just recopied our integral on a new page and we're ready to go with our integration. So we've got 1/2 times, we're going to do our integration, get negative x to the 5th over 5 plus 81x, and we're going to be subbing in 3 and then negative 3. So we're going to keep this 1/2 out in front. Plug in 3, we're going to have minus 243 over 5 plus 243. And then we're going to be subtracting off the value at negative 3. So 243 over 5 minus 243. And then we've still got square brackets there. So if we put all this into the calculator, this comes out to 972 over 5. So remember, what we just calculated in this step was the integral over our region of something that looked like y sub e times dA. Now in our final step, what we need to do to get y bar is we need to say, well, y bar is 1 over the area times this integral that we just calculated. So this is a quick step because what we're going to do is we're going to take this integral that we just calculated and we're just going to divide it by the area. So the integral that we just calculated, 972 over 5, and then we can take a look back at step 1 and figure out what was the area that we calculated. And here it was, we found the area to be 36 at the end of step 1. So we're just going to go 1 over 36 times the integral that we just calculated. And 972 divides nicely by 36. So this just works out to 27 over 5. And that gives us the y coordinate of the centroid. So to finish the problem, usually we just summarize it by saying what are the x and y coordinates of the centroid of our region. Remember, right at the beginning of the problem, we said x bar would be 0 by symmetry. So we knew that pretty much right off the bat. And then we've just done all this work to find y bar, which was 27 over 5. So let's draw a quick sketch of our region and just see if that seems reasonable. So we had this region that was bounded by the parabola and then y equal 9 at the top. And we said, well, the coordinate of the centroid is going to lie along this center line where x equals 0. And how far up is it going to be? Well, 27 over 5 is like 5.4. So it's sitting maybe right about there. So to me, that seems reasonable from a geometry point of view because our metal plate is getting wider at the top. So that shifts the center of mass up a bit further than halfway up. So let's take a closer look at this formula, y bar equal 1 over the area times the integral over the region of y sub e times dA. You can think about this just from the point of view of units. So dA is a little chunk of area that would have units meters squared. YE is the average y coordinate on a slice, will be measured in meters. And then out in front, you're dividing by area. So that would have units of 1 over meter squared. So when you multiply all these things together, 1 over meter squared times meter squared, you do end up with units of meters, which makes sense because we're getting a y coordinate for our answer. In this next problem, we're looking at the region bounded by y equal root x and y equal x squared, and we want to find the centroid. Okay, so let's draw a sketch here. So let's say this is our x value 1, this is our y value 1. So our square root function passes through 0, 0, and 1, 1, but it's a relatively slow growing function, does something like that. So that's our y equal root x. And then y equal x squared also passes through 0, 0, and 1, 1, but it's got this sort of a shape. So that's y equal x squared. So the region that we're talking about is the region enclosed by those two curves there. Now, if we look carefully, we'll notice that there is some symmetry here. You could draw a dotted line, y equal x, and it turns out this region actually looks the same when it's reflected through this dotted line. The reason why that's true, if we think back to pre-calculus, it has to do with the fact that the square function and the square root function are inverse functions. So square root undoes a square and a square undoes a square root. And geometrically what that means is that the square root function and the square function are going to be exactly symmetric about this line, y equal x. What that means is that the center of mass is going to lie somewhere along this line being y equal x. Okay, so we don't know exactly how far along the center of mass will lie, but it's going to lie somewhere along the dotted line. And what that tells us is that y bar is going to equal x bar. We can say by symmetry. And that's great for us because that means we don't need to calculate both y bar and x bar. We just need to calculate one and we'll get the other one for free. So therefore, we're going to focus on finding x bar. So let's try to run through the 4 steps that we did in our previous problem. First thing we need to do is calculate the area of our region. So I would say vertical slices would work just fine here. That's usually our go-to approach unless we have some reason not to use vertical slices. Okay, so let's do vertical slices and we'll say area A is equal to the integral of, well, whenever we do vertical slices, y top minus y bottom times dx. All right, so let's put the details on here. Just from looking at our sketch, our y top is root x, our y bottom is x squared. We've got the dx at the back telling us that we're integrating with respect to x, and that means it's x values that are going on the integral. So we're going to be integrating from 0 to 1. So x to the 1/2 after we integrate becomes x to the 3/2 times 2/3. And then we've got minus x cubed over 3. We're going to evaluate at 1 and then at 0. So plugging in 1, we get 2/3 minus 1/3. And then we subtract off the value at 0. So in other words, our area comes out to 1/3. So second step of any problem involving centroids, this is where you need to find x sub e and y sub e. In most problems, you don't need to find both. You just need to find one of them. So in this problem, it's x bar that we're trying to calculate. In other words, it's x sub e that we need. If we were also trying to compute y bar, then we would find y sub e as well. We need to think about whether we are using vertical or horizontal slices in our problem. We already decided in step 1 that we're using vertical slices. So we'll just draw a picture of that. So zoom in on any vertical slice here. Let's say we zoom in on this one. And just think about what is the average x value going to be along that slice? Well, it's just going to be x, because on a vertical slice, the x value is not changing. As we move up and down that slice, the x value is not changing. So x sub e is just x. If we needed y sub e, we would say it's y bottom plus y top over 2, but we don't need that for this problem, so we won't worry about that. Okay, and then step 3, we're going to compute the integral of x sub e times dA, and we're going to be integrating over our entire area A. So in plugging into this integral, there are 3 things we're going to think about. We'll think about what numbers need to go on to the integral. We'll think about what is x sub e, and we'll think about what is dA. So x sub e, we just figured that out in step 2, it's just x. To get dA, just look back at step 1. dA is just a fancy name for whatever you integrated to get your area. So this is dA. If you think about it geometrically, dA is just the area of a vertical slice. So it's root x minus x squared times dx. That's our dA. And then we know we're integrating with respect to x, so we can just look back at our sketch to figure out what numbers need to go on to this integral. So just scroll back to our original sketch to remember that, and we can say, oh yeah, we're integrating through x values 0 to 1. So those are going to be the numbers that go on our integral here. Okay, and then we're good to go ahead with our integration. So geometrically, what's happening here is the integral is summing up the area of each vertical slice times the x value that's represented on that slice. So that's giving us a quantity in meters cubed. And then at the end of the problem, we're going to divide that by area. And what that will leave us with is a weighted average of the x values across our whole region. In other words, it'll give us the x coordinate of our centroid. So to get our integration done, let's clean up our integrand. We've got the integral from 0 to 1 of, if we actually expand this out, this would be x to the 3/2 minus x cubed. And then doing our integration, we'll have x to the 5/2 times 2/5 minus x to the 4th over 4. And we're going to evaluate that at 1 and then at 0. So plugging in 1, we're going to have 2/5 minus 1/4. And then we'll subtract off the value at 0, which is 0. So just creating a common denominator here, this is going to be 3/20. So at this point, we're in units of meters cubed. Remember, we've summed up the areas of all these slices times the x-coordinate of the slice. So to get an answer in meters, we now need to divide this by area. So this is going to be our final step. Call this step 4. We can say x bar is 1 over the area times this integral that we just calculated, which was the integral over our region A of xe times dA. And we've got all the pieces of the puzzle now. We just need to scroll back through our various steps. So let's look back at step 1 to see what the area was. Looking back at step 1, oh yeah, area was 1/3. So if we want to divide by 1/3, that is like multiplying by 3. Okay, and then that needs to get multiplied by this integral that we just calculated in the last step. That integral had value 3/20. So overall, x bar comes out to 9/20. And then to finish the problem, we usually like to give both the x bar and the y bar value. Remember, we said right at the beginning of the problem that y bar was equal to x bar by symmetry. So now that we've got x bar, we automatically know y bar as well. They're both equal to 9/20. So if we just draw a quick sketch of our region along the line y = x, but how far along is it? Well, it's not actually halfway along, it's just under halfway along. So right about there is our center of mass for that region. So this will be our last problem for this video. We're going to find the region, or we're going to look at the region bounded by y = 3 minus x, y = root x minus 1, and y = 0. And we are going to find y bar, so that's the y coordinate of the center of mass for that region. So let's start by making a detailed sketch. We can sketch the line y = 3 minus x first. So that's going to have a y-intercept of 3, and it's got a slope of -1. So there's our line there. And then the other thing we could do is we could plot the square root function. So for that, let's make a table of values. Let's think about what x values we would like to plug into this, given that y is equal to root x minus 1. Okay, so you could plug x = 1 into that. Then y would be root 0, which is 0. You could plug x = 2 into that. Y would be root 1, which is 1. And you could plug x = 5 into that. Then y would be root 4, which is 2. So those are some of the nice x values to plug in there. So let's try to plot that. Maybe I'll plot that in a different color. So when x is 1, y is 0. When x is 2, y is 1. And then when x is 5, y is 2. Okay, so our square root function is doing something like that. So the region that we're looking for, the region bounded by the line, the square root function, and then remember y = 0 is the x-axis. So we're talking about this little region in here, this blue region. We want to find the y-coordinate of the center of mass for that region. So first thing I would point out here, there's no symmetry. There's no horizontal or vertical or diagonal symmetry here. But the problem does not ask us to find the entire centroid. It's just saying find y bar. So we do not need to find x bar to solve the problem. That's good. That's going to cut down on the amount of work that we need to do. So let's think about the steps that we want to run through. So I might list out the steps here just so we're clear. So first thing we're going to do is find the area. Second thing we're going to do is figure out x sub e and y sub e. Now, if it's just y bar that you're trying to find, you don't care what x sub e is. You only care about y sub e. And then once we've got that, then we'll calculate a second integral, which looks like integral of y sub e times dA, integrating over the same area as we did in step 1. And then once we've got that, then we'll take that integral and we'll divide it by the area. So the big question you have to ask yourself in step 1 is, are we using vertical or horizontal slices? And whatever decision you make in step 1, that's going to carry through the problem, because that's going to determine how you calculate y sub e. It's going to determine how you calculate your integral in step 3. So it's worth making a careful choice about that, and let's focus on that decision here. So let's look at our region. We've got the picture on the screen here. So if you tried to do vertical slices, sometimes the top of that slice would be hitting the square root function, and sometimes it would be hitting the line. That's not good. So that means vertical slices are not going to work well here. So now let's consider horizontal slices. Let's think about filling in our region with some horizontal slices. Every horizontal slice would be hitting the square root function on the left and the line on the right. So that seems like that would work great. So we're going to use horizontal slices for this problem, and we're going to practice that approach. All right, so let's think about area. Flashback to area with horizontal slices. So you're integrating whatever the area of a horizontal slice is. That's x right minus x left times dy. So in order to plug into this integral, we need to do a little bit of side work. So let's go back to our sketch, and we're going to think about x right and x left in a little bit more detail. So this function had equation y equal root x minus 1. Let's solve this equation for x. So we would need to square both sides. We'd say y squared equals x minus 1. And then we could say y squared plus 1 is equal to x. And what this is giving us is the formula for x left. So x left is equal to y squared plus 1. Okay, and then let's try to do the same thing for x right. So we're going to do that here. X right for each of these slices is coming from the line. Okay, so if we just move some things around, x equals 3 minus y, that's going to be our x right. X right is 3 minus y. So something that's always a little bit tricky when you're dealing with horizontal slices is you always have to do this algebra of solving for x in both equations so that you can figure out what your x right and your x left are. And then with that, I think we're ready to plug everything into our integral. So we're integrating, we're going to go 3 minus y, which is our x right, and then we're going to subtract off x left. So we need brackets there. We need to go minus y squared plus 1. That's all going to get integrated with respect to y. And because we're integrating with respect to y, it's y values that are going to go on the integral. So we can look up at our sketch here and just see that the y values that we're going to be using in this problem will be from 0 to 1. And then we can clean up our integrand and do our integration. So just cleaning up the integrand here, we'd have 3 minus y squared minus 1. And I'm just going to take that 3 minus 1 and write it as 2. So really our integrand is 2 minus y squared, and we're going to integrate that with respect to y. Okay, that seems reasonable. So doing our integration, 2y minus y squared over 2 minus y cubed over 3. And we're going to evaluate at 1 and then at 0. So plugging in 1, we get 2 minus 1/2 minus 1/3. And then subtracting off the value at 0, which is 0. All right, so then we could put everything over 6, and that would give us 7 over 6 for the area. Now we know from experience, from having done 2 of these problems before, that later on in the problem, we're going to want to know what dA is. So if we could highlight that in this step, that might make things a little bit quicker when we come back. So dA is just shorthand name for whatever you're integrating to get your area. The last step where we had the integral sign on here was this one. And so this stuff behind the integral is our dA. So we'll use that a little bit later in the problem. Step 2 is to think about XE and YE. So I'm just going to draw a picture to remind us what that represents geometrically. So we've got this region here. Left half formed from the square root function, right side formed from a line. Our region looks something like this. And we decided that we were going to fill in this region using horizontal slices. So just zoom in on a typical horizontal slice like that. XE and YE represent the average X and Y values on this slice. So for a horizontal slice, Y sub E is just going to be Y. Because if our slice is going horizontally, the Y values are not changing over the course of that slice. So the average Y value is just going to be Y. Whereas the average X value, you would take X left plus X right and divide that by 2. Now we don't care about X sub E in this problem, so I'm not going to worry too much about that. We just need to know here that y sub e is equal to y. And I think just because this is our last problem, I might, just for the sake of a complete discussion, talk about vertical slices at the same time. So imagine you were doing a vertical slice problem. Zoom in on one of your vertical slices. If you needed x sub e, you would say, well, what's the average x value across my slice? We would just call that x, because all the points on this vertical slice have the same x value, whereas y sub e would be your average y value across your slice. You'd have to take y bottom plus y top over 2. So really, for a complete understanding of centroids, you want to be comfortable with these 4 formulas. And then in each scenario, you just figure out, oh, are we doing horizontal slices in this problem, or are we doing vertical slices? We decided we're doing horizontal, so we don't care about this bottom situation. And then, are you doing y bar or are you doing x bar? If you're doing y bar, it's only y sub e that you care about. So here we are in step 3. This is where we calculate the integral of y sub e times dA, and we're integrating over the entire area A. All the pieces of the puzzle would be in your previous 2 steps. So we decided that y sub e is equal to y, and we can get dA from looking back at step 1. So dA was just whatever we integrated in step 1 to get the area, and we actually decided to highlight that to save us a little bit of time. So it's 2 minus y squared times dy. Okay, then we can plug everything in here. So we're going to be integrating y times 2 minus y squared times dy. And this dy at the back is important because it tells us that it's going to be y values that are going to go on the integral. So 2 ways to approach this. One is you can just scroll back to the original sketch and figure out what y values you're integrating through. So that would be 0 to 1. Or maybe even easier is you can say, you're just going to be using the same y values as you used in step 1. So before doing our integration, we're just going to clean up our integrand here. So we'll have the integral from 0 to 1 of 2y minus y squared minus y cubed. We're going to integrate with respect to y. So doing the integration gives us y squared minus y cubed over 3 minus y to the 4th over 4. And we're going to evaluate this then at 1 and 0. So plugging in, we're going to have 1 minus 1/3 minus 1/4, and then subtract off the value at 0, which is 0. Okay, so let's put everything over 12, and this is going to come out to 5 over 12. So remember that after step 3, you're not quite done, because what you've got here is a quantity that would be measured in meters cubed. In order to turn this into meters, we still need to divide by the area, and then we'll have our answer. So last step, step 4, we're going to say the average y value over our entire metal plate is what we get if we go 1 over the area times this integral over our area of y sub e times dA. And we've got all the pieces of the puzzle now to finish off this computation. So just look back at step 1 and figure out what the area was. Let's scroll back. The area was 7 over 6. We want to divide by that. So that's like multiplying by the reciprocal. We'll say 6 over 7. And then that gets multiplied by this integral, which is what we just calculated in step 3. So that integral came out to 5 over 12. Great, and then we can do just a little bit of simplifying here. So cancel a factor of 6 from the top and the bottom, and we can say this is 5 over 14. So that's our final answer. Y bar is equal to 5 over 14. Notice that we were not asked to find x bar in this problem. There was no symmetry in this problem, so if we wanted to find x bar, that would be a completely separate calculation. So main takeaway from these centroid problems, let's make sure that we understand the 4 steps that are involved in calculating x bar or y bar. And let's also make sure that we're comfortable with figuring out x sub e or y sub e, depending on the problem. So that's all about centroids of thin metal plates. Thanks for watching.